So for oblique asymptotes, this is the situation where the higher degree is on top. Higher degree is on top. Now, if you can see here, this is an x squared and this is an x. The higher degree is on top. 2 is greater than 1. And so this graph and the end behavior as it goes off to larger values of x and smaller values of x, the extremities of the x-axis, you will see that the graph takes off and goes without bounds. So I have it graphed on the Desmo app. If you don't have the Desmo app, it's fantastic. But here is that function, f of x equals x squared plus 7x plus 12 over x. And as you can see, it is taking off as x get larger, and it takes off on this diagonal line going really high. What you'll also notice is it takes off going very far to the left, going down this way. Can't mark in this, but it goes down. But what I want you to know is there's something similar about the angles of those two lines. They go off to infinitely big and infinitely small. And it's not coincidence. And we can actually see exactly the angle at which it's going. We can see the asymptote that those get infinitely close to without ever touching. And so how we do that is by actually doing what this says. So you can look at this as a fraction, but you can also look at it as a division problem. X squared plus 7x plus 12 divided by x. Now, if I do long division, x squared plus 7x plus 12, and I actually do the division divided by x, I say x times what is x squared, and the answer is x. X times x is x squared. I subtract and bring down. And I say x times what is 7x, and the answer is 7. Now, what's nice about this is we don't actually care about the remainder. There will be a remainder here. The remainder is going to be 12. But we don't care about the remainder. We let that fall off. But this right here, x plus 7, if we look at that as an independent function, as f of x equals x plus 7, here's what's really crazy. That value we got by actually doing this as a division problem, the linear function x plus 7, if I go back and graph that, let's see here. So f of x is equal to x plus 7. What you'll see is that line x plus 7 is the asymptote. It very specifically is the oblique asymptote or the slanted asymptote. And this can get really crazy. There's an example in your book where you do the division and it turns out to be a quadratic, and the quadratic itself perfectly hugs the curves. And so what I want you to see is math is mind-blowingly amazing. We can see the asymptote for this rational function by doing the division and looking at what's left, that linear equation x plus 7. So coming back to this, you can have a function where the degree is higher on top, and higher on top means that there is no horizontal asymptote, that the function itself takes off and goes infinitely high and infinitely small, but it does so with very specific parameters. It goes and gets infinitely closer to the line x plus 7, but that is an asymptote. It never actually gets there.